Hello everyone, my name is Chiara. I'm a postdoc at the University of Louvain in Belgium, where I'm part of the core group. And in my seminar, I will present how we can implement stochastic inflation by using stochastic trees, and how we can use this framework to study primordial black hole formation in the early universe. The scenario I'm interested in is the one where inflation produces exceptionally large primordial curvature perturbations that may later collapse and form primordial black holes. And the goal of my seminar is to show how we can study such large perturbations without relying on cosmological perturbation theory, but using a non-perturbative framework. A possibility is given by the separate universe approach, according to which the universe, at large scales, is described as an ensemble of independent, locally homogeneous and isotropic patches of Hubble sides that evolve according to the background equation of motion, but starting from different initial conditions. In this separate universe framework, then, the curvature perturbation zeta we are interested in is nothing but the local amount of expansion experienced by those patches. And this is what is called the delta n formalism, where n here is the number of equals, namely the logarithm of the scale factor. Moreover, if we have large perturbations, then it may also be necessary to account for backreaction on the inflaton background dynamic. And this can be done in the stochastic inflation formalism. Stochastic inflation basically is an effective theory for quantum fields during inflation, and therefore for the inflaton itself, that are cosgrained above the Hubble radius, in a way that subhorizon modes are still small amplitude fluctuations that we can describe with cosmological perturbation theory, but on super-Hubble scales, we have large amplitude fluctuations that we describe with stochastic inflation. However, because of the shrinking of the comoving Hubble horizon during inflation, quantum subhorizon modes constantly cross the Hubble radius and join the cosgrained sector of the theory. So in practice, they act as an effective contribution to the cosgrained field. As a consequence, this cosgrained field then follows a classical theory which is stochastic, and so is described by Langevin equations. Here, for instance, we have the Langevin equation for the cosgrained inflaton, and we can see two terms on the right-hand side. The red term is the usual classical drift term induced by the gradient of the inflationary potential function, but we also have a green term which is a noise that corresponds to the continuous inflow of subhorizon modes into the cosgrained sector of the theory, and it acts as a quantum diffusion effect. Of course, the properties of this noise depends on how we cosgrain our field. If we consider a sharp window function in Fourier space, then the noise will be wide with no correlation over time. So our process describes a Markovian evolution, and also depends on the cosmological perturbation theory we use in the subhorizon sector. If we use cosmological perturbation theory at leading order, then we have a quadratic theory and it predicts a Gaussian noise. So in what follows, the psi here will be a white Gaussian noise with vanishing mean and unit variance. Now, if we use the stochastic inflation framework to describe the amount of expansion in those patches and also their statistical properties, then this gives rise to the stochastic delta n formalism, where the duration of inflation in those separate universe patches becomes a stochastic variable that is usually denoted with this calligraphic n. So in practice, the idea is that if we start from a certain initial field configuration, we can have different realizations with different durations because of this quantum diffusion, and therefore the duration of inflation is not deterministic anymore, but is stochastic. This stochastic duration has its own probability distribution function that is called the forced passage time distribution, because we are interested in the first time the end of inflation is reached, and it can be obtained by solving the adjoint Fokker-Planck equation associated to the Langevin equation. And finally, once we have solved for this stochastic duration of inflation, then, thanks to the delta n formalism, we can infer the statistics of the cosgrained curvature perturbation zeta, and this is a fully non-perturbative result. Now, a generic property of this distribution, it can be written as a sum of decaying exponential functions, where the decay rates are ordered according to this hierarchy. So if you're interested at large values of n or of zeta, then we can approximate the sum with the first term only. And this leads to exponential tails that are fully non-Gaussian and also that describe a type of non-Gaussianity that cannot be obtained by perturbative parametrizations that are done, usually in cosmological perturbation theory, like FNL-GNL expansion. So this is basically the standard stochastic delta formalism that has been widely used to predict the statistics of large fluctuations during inflation, and it predicts more abundant high curvature regions than what cosmological perturbation theory will tell, with consequences on tail-sensitive events like primordial black holes. The formalism relies on stimulation of independent large realizations, first passage time analysis, theory of conditional probability. It has the advantage to have analytical and semi-analytical results in simple toy models. However, it also is restricted to a set of cosmological fields and models. And therefore, in what follows, I will present an alternative and complementary way, which is how we can implement stochastic inflation and the stochastic delta program on stochastic trees by modeling the inflationary expansion as a branching process that here is considered to be binary, but this comes without loss of generality. So as a reference, let us have in mind a single field slow roll model of inflation. This is the Langevin equation for the inflaton field, and xi is a white Gaussian noise. And we are interested in cost-graining perturbation fields over regions of size sigma h to the -1, where sigma is a small parameter that sets the cost-graining scale well above the Hubble radius. So we can consider to have as time n equals 0 a single patch I, and as time proceeds here from top to bottom, the volume of this region will grow, and after a time delta n, which is log 2/3 for binary processes, it doubles in volume. And so it creates two new patches L and M. So in practice, we start from the field configuration phi I in this patch, and we solve the Langevin equation twice over a duration delta n to get field values phi L and phi M. And on inflationary backgrounds, these two children patches have no future causal contact, and in this way, the separate universe picture over which we implement stochastic inflation is conserved. This structure is an elementary vertex that can be repeated in a recursive way because each vertex then gives rise to children patches and so on and so forth, up to have a whole binary stochastic tree that is made of nodes and branches. And in principle, if inflation never stops, the tree will grow indefinitely, but we know that inflation has to stop. And this occurs in the final nodes that are the patches colored in green that we can imagine of as leaves of the tree. And stochastic trees of this type can be efficiently generated numerically in a recursive way because each vertex gives rise to a subtree that can be processed independently. And we have developed a code which is called Forest that stands for Further Recursive Exploration of Stochastic Trees that is also publicly available, that takes as an input an inflationary potential function, its derivative, some boundary conditions for the Langevin equation, and it creates and explores a large number of stochastic trees of this type to deliver relevant statistics for cosmological fields and also for primordial black holes. Therefore, stochastic trees are an alternative way with respect to lattice simulation of inflation and numerical relativity simulations, and differently from lattice codes, they do not proceed on a fixed background because new spacetime units naturally emerge as the trees unfold, and therefore this naturally incorporates metric fluctuations. Now let me explain how we can reconstruct the curvature perturbation from stochastic trees. So let us imagine to have a stochastic tree realization of this type. Then, for each node I of the tree, is straightforward to compute the physical volume of the region emerging from it, because it's just the sum of the volumes of the set of leaves descending from it, where the volume of a leaf is just the exponential of this amount, where this n here is a first passage time from this node up to the final leaf along this branch. We can also compute this quantity W, which is the number of e-folds from this node, volume averaged over the set of leaves descending from it. And now, if we imagine that this tree is the whole observable universe of an observer that is performing measurements on the end of inflation hypersurface, then for them, the curvature perturbation coarse-grained on a single leaf is just the deviation of the local amount of expansion from the root node up to the leaf, with respect to the average over the whole observable universe. And this can be easily generalized if we want to coarse-grain the perturbation field over a region that encompasses more than one single leaf. Stochastic trees are also ideal tools to harvest primordial black holes, and let me just make a few comments. We know that primordial black hole formation takes place in region of high curvature, but using the curvature perturbation zeta is not always well justified, especially if we have large quantum diffusion effects. First, because it's defined with respect to a certain observer, and second, because it's not local. Indeed, it contains averages through this W1 over regions that can be very distant from the region we are looking for. And this is also why other fields are considered usually in literature when talking about primordial black hole formation, like the density contrast or the compaction function, because they are proportional to the Laplacian of the curvature perturbation. So they feature a suppression of large-scale contributions. And in stochastic trees, we use the idea of the coarse-shelled curvature perturbation as a proxy for the compaction function. So in practice, if we consider the elementary vertex of the stochastic tree, we define the curvature perturbation in a certain node, for instance L, relative to its local background I. And if we define the coarse-shelled curvature perturbation as this difference. And why it's called coarse-shelled curvature perturbation is because if we picture the regions emerging from the parent node I and the child node L as two concentric spheres, then the coarse-shelled curvature perturbation is nothing but the curvature perturbation coarse-grained over the shell between the two regions. In practice, we consider that nodes for which this coarse-shelled curvature perturbation is larger than a certain critical threshold will collapse into primordial black holes. And if we assume formation of primordial black holes in radiation dominance and a threshold on the compaction function of 0.5, we find that the threshold on the coarse-shelled curvature perturbation is 1/2 the logarithm of the ratio of the volume emerging from the parent over the volume emerging from the child. And in practice, we find in stochastic trees that the collapse into primordial black holes happens at most asymmetric nodes, namely in nodes for which the volume emerging from two siblings is really asymmetric. This is also why this coarse-shelled proxy can be seen as an unbalanced index. We discover in stochastic trees that primordial black hole formation happens at trees that show a high level of asymmetry. So in the time that remains, let me just show an application of stochastic trees to a simple toy model that we call the quantum well, where there is a region exactly flat at small scales along the inflationary potential function, where the dynamics is driven by quantum diffusion. Instead, outside this region, the dynamics is classically dominated by the gradient of the inflationary potential. At the beginning of the well, there is a reflective boundary, so when the field enters the well, it cannot climb up into the classical region. And at the end of the well, there is an absorbing boundary, so when the field reaches this point, it has to exit the well, and this usually corresponds to the end of inflation. Let me mention that in this model, there is a single parameter that controls all predictions, that is this mu squared, which is the ratio of the width of the well squared divided by the potential height in Planckian units, and is an indicator of quantum diffusion. If mu is large, we expect more quantum diffusion effects. And in particular, there is a value of mu over which we have eternal inflation. Namely, the mean volume is divergent and the tree will grow indefinitely. So in practice, in what follows, we will work for values of mu that are below the critical value for eternal inflation. So what we did is to generate a large number of stochastic trees in this model of the order of 10 to the 10, 10 to the 11, and then we reconstruct relevant statistics over the entire tree population. Here I'm showing the distribution of the volume and of the volume average number of EFOLs for different values of the mu parameter. We see that both distributions show a relatively small mean value and a power law behavior that is then followed by exponential tails that are heavier as mu increases, as we expect because we increase quantum diffusion effects. In particular, for the volume distribution, we find a power law behavior with power minus 3/2 that is followed by an exponential tail, where this z star here is a negative number that corresponds to the rightmost pole of the generating function of the volume. And when mu goes close to the critical value for eternal inflation, that is the black dashed line in this plot, then the volume distribution has a poor power law decay. And really interestingly for us was to discover that those results are expected from bacteria models, namely from Galton-Watson processes that are used in biophysics to study degeneration, evolution, and extinction of bacteria population, where bacterial extinction corresponds to eternal inflation in our case. We also reconstructed statistics over the whole leaves of the entire tree population, and here I'm showing the volume-weighted force passage time distribution from which the distribution of the curvature perturbation can be reconstructed for different values of mu, where again we find the power law behavior followed by exponential tails. We also compare the result of our numerical procedure with the exact analytical prediction that is available in this model, that is the black dashed line result, that also serves as a strong benchmark of our numerical code. Finally, as I said before, we can also use stochastic trees to harvest primordial black holes, and here I'm showing a realistic tree that we obtained in this model that contains 5 primordial black holes that corresponds to the collapse of the regions on the end of inflation hypersurface emerging from the nodes that are circled in red. So let me mention that when we look for primordial black hole formation, we start from the end of inflation hypersurface, and at each branching, we check if the condition for the collapse is satisfied as we climb up the tree, up to the root. And if it is, we mark the node in black. And it's really common to find nested PBH formation along a branch that is really similar to the cloud-in-cloud problem, namely to the formation of smaller structures inside the larger ones. And since here we only keep the highest or the oldest nodes in the PBH inventory, then stochastic trees naturally account for cloud-in-cloud effect. That is a nice property of them. And finally, let me just show some plots for the distribution of primordial black holes in this model. On the left, we have the fraction of the universe at the end of inflation that will eventually collapse into primordial black holes as a function of mu. We see that this fraction increases with mu, and close to the critical value, almost all the universe is made of primordial black holes. We also compare the result of our numerical procedure, that are the blue dots, with a simple analytical estimate that is based on a Press-Schechter calculation on the curvature perturbation. We see that the two results have the same behavior, and the difference is of about 1 order of magnitude. And this is quite remarkable given the differences between the two approaches, and it also shows that predictions that are made usually in the stochastic delta M program in the literature can be considered fairly reliable. Finally, on the right, we have the mass distribution of primordial black holes in this model, again for different values of the mu parameter. We see that as mu increases, the peaks of the distribution shift to larger masses, and we again have power law behavior followed by exponential tails. And when mu increases and get closer to the critical value of eternal inflation, we see that the power law regime is across a larger mass range. And it has a behavior that can be fitted, and it is with a power law with an exponent minus 2/3. Okay, so those were my last plots. So let me just move to some final remarks. So stochastic inflation can be efficiently implemented on stochastic trees if we model the inflationary expansion as a branching process, and we have seen that statistical properties of curvature perturbations and other cosmological fields are embedded in the tree structures. Stochastic trees are also ideal tools to harvest primordial black holes. They also directly address the cloud-in-cloud problem. And in general, we have seen that power law behavior followed by exponential tails characterizes statistics over the trees and over the leaves, and also the mass function of primordial black holes in simple toy models. So, of course, what I presented so far was an application of stochastic trees to simple toy models and also to one-point distributions. And there is much more to explore, for instance, considering much more realistic models, ultra-slow roll scenarios, and also multiple point statistics, higher order correlators, clustering property of primordial black holes, and on some of these topics, we are working now with my collaborators. So with this, I really thank you for the attention, and I'm looking forward to meet you during the conference days.